Good afternoon, everyone. We are here today with two speakers, Dr. Shelia Newman, and Dr. Andrew Wilson. And I will just very briefly introduce each of them and then pass the floor to our speakers so they can conduct their panel. Andrew Wilson, he's a knowledge exchange associate at the University is a postdoctoral research associate from the Aerospace Center of Excellence at the University of Strathclyde in Glasgow, United Kingdom. His primary research focus relates to the integration of life cycle sustainability assessment into the concurrent engineering process of space missions. Andrew has been involved in every space mission design session conducted at the University of Strathclyde, where he acted as systems engineer, team leader, and eco-design expert. He received a first-class honors degree in environmental management from Glasgow Caledonian University in June 2015, and a PhD in mechanical and aerospace engineering from the University of Strathclyde in July 2020. Andrew has also had short spells working with the United Nations Environment Program and the European Space Agency's Clean Space Office. Andrew was awarded the 2018 Young Scott Environment Award and was named one of the Junior Chamber International's 10 Outstanding Young Persons of Scotland in 2019 for his contribution to scientific and technological development. Thank you, Andrew, and welcome. Next, we'll have Dr. Sheila Newman. She is an intelligence studies professor at American Public University System. She got her doctorate in 2018 from the University of Texas at Arlington, and her doctoral research was focused around the US commercial space transportation activities and the environmental life cycle assessment method in the ISO 14040/14044. Sheila served in the US Air Force as a bioenvironmental engineer for over 20 years, evaluating the occupational health and environmental issues related to aircraft activities, to include hazardous materials and system engineering aspects. Her test and evaluation work on F-22, B-2, and F-35 allowed the health hazards and environmental issues to be identified and managed before these aircraft were fielded. She also was an intelligence analyst and supervisor of analysts at the Defense Intelligence Agency, Federal Bureau of Investigation, and the Department of Homeland Security for over 14 years. Sheila's intelligence focus areas were weapons of mass destruction, biotechnology, environmental health, and analytic methodology. Thank you both, and now I pass the floor to you.
Thank you very much, Daniel, for the introduction. I assume you can all hear me okay? Great, perfect. So first of all, I hope you can all understand me through the thick Scottish accent. I know it's not always the easiest accent to understand, so I'll try and speak slowly and clearly. So today we're going to be talking about space and life cycle assessment, and particularly how it is standardized through ISO 14040 and how that can be tailored to space applications itself. So what we want to talk about today is give you an introduction. So what is the background, what is the context for why we want to apply life cycle assessment? What is environmental life cycle assessment, and how is it standardized? We'll then give you a little bit of historical context from the point of view of how it has developed so far within the space sector. And then we will hand over, very importantly, to the work that Sheila has done, where she will look at US launch activities and why use a life cycle assessment for US launch activities. And then she'll take you through a step-by-step approach for a life cycle assessment study that she ran for one US launcher. We'll then kind of go on to talk about, does this assessment actually go far enough, or do we need to advance it to something that's a bit more comprehensive, that considers something other than just the environment? How do we integrate it into the space mission design process? And then finally, we'll conclude on why should the US space industry care at all about what we're actually speaking about, and we'll give some recommendations on that. So first of all, what actually is the problem here? Well, traditionally speaking, environmental impacts of space missions have been missed out from key legislative and regulatory requirements. One of the best examples I can give on this is the Montreal Protocol on substances that deplete the ozone layer. In the 1980s, when this was introduced, it really did target chlorofluorocarbons from refrigerators and other ozone depleting substances that was creating a hole in our ozone layer. Now, this protocol actually completely missed out the space sector, despite the fact that it's the only form of man-made pollution that injects ozone-destroying compounds into each layer of the atmosphere through our launches, particularly the stratosphere where the ozone layer resides. And it's not just this one bit of legislation, there are several. Within Europe, there's the Restriction of Hazardous Substances Directive and the Waste from Electrical and Electronic Equipment Directive. And these grant exemptions for certain substances within the space sector. So the space sector is actually exempt from many other environmental legislation. But in recent years, we've seen renewed international commitments towards environmental problems. For example, we've seen the implementation of the Paris Agreement. We've seen the adoption of the 2030 Agenda for Sustainable Development. And within Europe, we've even seen the European Green Deal. And in line with the change in the public's opinion and how they want to address or go towards environmentally benign products, there's a real shift in emphasis. And this has really been highlighted by the billionaires recently that we have seen launching themselves into space, which has really brought this issue into the public limelight. So there's really now an emphasis on actually, can the space sector address their own impacts? How can this be done? Well, it has already been identified by the European Space Agency as life cycle assessment being the most appropriate tool to measure such impacts. So what actually is environmental life cycle assessment? Well, it's simply an environmental management tool. So under the ISO, which stands for the International Organization for Standardization, they have a series of environmental standards under the ISO 14040 series. Two of these are ISO 14040 and ISO 14044. These are really the standards that dictate LCA and how it is applied. So what is the difference between the two? Well, ISO 14040 provides the principles and frameworks for life cycle assessment, and ISO 14040 provides the requirements and guidelines. In simplistic terms, what this means is that if you're interested in learning about LCA or you're the manager, you would read ISO 14040 because it's aimed more at a managerial audience. In comparison, if you're looking to actually do an LCA yourself, you would read ISO 14040 because that is aimed more at a practitioner audience. So life cycle assessment in itself looks to scientifically quantify the life cycle environmental impacts of a product, a process, or a service across its entire life cycle. So that's everything from raw material extraction through the production and manufacturing, the transportation, use, and eventual end of life. And this is very important because it allows decision makers to not only quantify the impacts of products, but also identify and then mitigate potential hotspots or areas of large environmental concern before they actually occur. And similarly, we can actually match these life cycle stages to a space mission. So for example, looking at pre-phase A all the way to phase C during the design phase, the qualification and production in phase D, the launch and commissioning in phase E1, utilization in phase E2, and then the end of life in phase F. On this slide, we can see the life cycle assessment framework as outlined in the ISO 14044 standard on the left. So this all begins with a goal and scope definition, and this really dictates what the focus of your study should be. In this, under this umbrella, there's very many considerations that we should look at. So who is the intended audience? What is the purpose of the LCA? but very importantly, what is the functional unit? And the functional unit means it's a unit that we can refer all environmental impacts to, so a quantified reference of performance. And again, we also need to look at the system boundary. So this is what is included within our study and what we exclude. I need to be very transparent with this, so that we can publicly communicate our LCA at the end. Our inventory analysis, so this is the data sets or the data that we gather. So we need to collect data, compile it into inventory so that we could eventually run the impact assessment. Then the impact assessment quantifies the flows or the inputs from our inventory, which we can see on the right here could be energy, water, and raw materials. And then the outputs of this would be the usable product, water effluent, airborne emissions, solid waste, and other environmental releases. The impact assessment would essentially quantify these in terms of the damage they would do to certain impact categories. And as we can see, we can do this across the entire life cycle of the product, process, or service. And very important is the interpretation phase. This is actually trying to understand the environmental impact. So what is the result of this? Also running uncertainty analysis and reaching conclusions of your LCA. And this is an iterative process. So every decision you make really needs to refer back through each of the levels here as well. So a little bit of historical context here. So traditionally speaking, within the space sector, only environmental statements were actually conducted as a environmental impact assessment. And this was normally around the launch site of launchers, so it was only very localized impacts that were looked at. However, the European Space Agency to address this began working on life cycle assessment in 2009, and to the end of 2019 had completed 46 studies on the topic at around a cost of around 20 million euros. As a result of these studies, they developed a new framework for space systems to make the ISO 14040 standard more applicable to space systems, and we can see what this encapsulates here. So firstly, the ESA ELC handbook provides the preliminary guiding principles which should be applied when conducting a space-specific ELC at either system level or component level. It tailors the methodological rules contained within the ISO 14044 standard to be more appropriate to the space sector without risking non-compliance. And they're also orientated as closely as possible with the product environmental footprint approach, which is developed by the European Commission. And these guidelines are actually available to European stakeholders upon request. The ESA ELCA database was developed because space is a unique domain, meaning its application is not straightforward. Environmental extended input-output methodologies provide highly inaccurate results, whilst traditional process-based databases don't actually have sufficient coverage due to the unique materials and the environmental impacts of the sector itself. So as such, the new database looks to act as a consolidated and centralized source of data sets specific to space activities. And it involved hundreds of world experts to contribute to this and contains over 1,000 data sets. Currently, access to this database is only available under contract with ESA. And then finally, the ECO CDF tool is intended to integrate LCA with the database into the space mission design process. And this is because most environmental impacts are actually set by early design choices. So meaning it can be more difficult to modify later into the design process that they're identified. However, this tool is currently not functional or available to the public. However, this framework really has driven the application of space ELCA within Europe, and there has been other studies to advance this framework. For example, one of our colleagues called Dr. Thibault Maury looked at integrating space debris as a impact assessment method within this framework. And for example, us at the University of Strathclyde have looked at transitioning towards a sustainability assessment, which we'll talk more about a little later. But in terms of ELCA, very few studies have actually taken place in space technologies elsewhere, and this includes North America and Asia, which really brings into focus and the importance of Sheila's work, which she will now present to you.
Thank you, Andrew. So what are the environmental impacts in the United States of the launch of one commercial rocket into space? The US has launches into space, seems like almost every week. And this graphic here, it was developed by the US Federal Aviation Administration, and it shows the commercial launch activities from 1989 to 2021. And you can see that the commercial space industry has really skyrocketed over the past few years in the United States. As you look at the graph on the bottom, within the past 3 years, launches have increased. This calendar year, we've had 43 launches, and that's about 4.5 launches per month, which is about a launch per week. Next slide. So I began my research to focus on applying ISO 14040 to the launch of one rocket and to determine what the total life cycle impact would be from one launch within a 14-day launch window. So 2 launches per month. So listed here on the slide, it shows a few reasons why I chose to conduct an environmental life cycle assessment. The National Environmental Policy Act is been known to be the one of the areas that has not been fully realized yet has been the environmental area. And the National Environmental Policy Act is a current law that would provide some environmental assessment of the impacts for the space launches. But these EAs do not have all the required information that would get you from the cradle to grave understanding of environmental and related impacts of the total life cycle. The Federal Aviation Commercial Space Transportation Office is responsible for collaborating with those rocket launch partners in preparing and submitting those formal EAs. So because these EAs do not provide that cradle to grave, I wanted to use the ISO standard, which Andrew mentioned, the process for it, and is very good for looking at the total life cycle evaluation. There are data libraries within software such as SemiPro or OpenLCA that could be used, and I did use the SemiPro. So what I did was I did a study on one launch of a space vehicle to determine the potential environmental and other related damage impacts. So these ELCA augments the NEPA documents and analysis, but it doesn't replace it. So I conducted my research as a doctoral student in environmental engineering at the University of Texas at Arlington. Next slide, please. So I developed an ELCA for the launch of one space vehicle at the launch facilities. I decided to compare 2 rocket boosters, the expendable and the reusable, and then I also looked at comparing the propellants. I looked at using liquid oxygen as my oxidizer, and then the hydrogen, the rocket grade propellant, RP1, and liquefied natural gas as the other fuels. And then I looked at other consumables typically found at a launch complex of power, chemicals, and water. So I did an evaluation of each of these consumables one at a time, and then I did a combined evaluation of the one launch activity. So the systems boundary for this ELCA looks like this. Next slide. So what it was included in my system boundary, the consumables to include the 2 rocket booster types. For the reusable rocket booster, I selected the first stage to be used 20 times. And so that was the reusability part of the reusable rocket booster. The transportation for the consumables to the launch complex, and then specific materials for boosters composition as found on open source information. And then I looked at end of life, only looked at the wastewater back to the treatment plant at the launch complex. And then I assumed that the expendable rocket booster would basically drop into the ocean. So what was not included in my system boundary? Well, the materials for the launch pad infrastructure and the construction of the launch pad infrastructure. The other thing that was not included was the specific space fabrication and manufacturing processes for that expendable and reusable boosters. And the reason for that was a lot of the material or the information about those manufacturing processes were from proprietary, and weren't developed in data sets or the data libraries that I used. But I did use the components and their materials composition for those rocket boosters. I did look at disposal or the end products from the different outputs at the launch complex, and I did some estimations of that within my research. I decided to use the semi-pro software I mentioned, version 8.2.3, as my primary database for this ELCA. So once the system boundary was defined, I developed the generic rocket boosters. Next slide, please. I use systems engineering models to develop the components of the rocket booster for each stage. I developed it into 3 stages: a first stage, a second stage, and a fairing. And the second stage and the fairing were similar makeup and composition. And the first stage that was different for the reusable rocket booster was its extra propellant for landing, and then the landing legs and the grid fins. And I also made these first stage have 27 engines and the second stage have 1 engine. I did not have the direct information, as I mentioned, but I did use information from open source on SpaceX Falcon Heavy, the ULA Delta Heavy, and also Blue Origin for the makeup and the composition of these different stages of the materials, and also for the propellants. Not having a specific rocket booster did make it more challenging, but I was able to develop these generic rocket boosters to build an ELCA framework. Next slide, please. So to support this ELCA, I used the semi-pro, as I mentioned, and this slide provides a set of data input that I had built for products within semi-pro and its materials categories. For each of the consumables and the rocket boosters, I also built this level of input for semi-pro. And you have to make a decision about your impact methodology. So I decided to use Impact 2002 Plus for my input data to help determine those inputs for the damage assessments. And the inputs from Impact 2002 Plus are human health, ecosystem quality, climate change, and resources. And I also looked and considered the midpoints for the different impact methodologies. And so I thought that Impact 2002 Plus, with its midpoints, were relatively fit well with and represented well the rocket or the 1 launch example that I wanted to do my research on. And I also looked to see what the Department of Defense was doing with their life cycles of the weapon systems, such as the Navy ships and things like that. And they were using a similar type of endpoints as well. I also looked at, there's a couple other impact methodologies I looked at during my research, was Recipe and Tracy. Some of those are more US related. And I used those to compare to see what the results would be. And they seem to compare very well with that. So for the next few slides, I'm going to quickly go through my research results with semi-pro. I'm going to show you the rocket booster comparison without propellant, the propellant comparison, and the other consumables of electricity, water, and chemicals. And then I'll show you an ELCA, a strategic ELCA, which includes a comparison of an expendable and a reusable rocket booster with a hydrogen propellant. But I think these results should give some insight into the overall base case that I did for 1 launch every 14 days. Next slide, please. So as expected, the expendable rocket booster causes more damage impact on these 4 areas that you can see here. For future reusable components, though, minor tweaks can be made and to add more data to that, and it can also fit into the framework that I developed. But you can see, as with cost, reusability is a key factor with cost and also in reducing environmental impacts. Next slide, please. The next comparison is the fuels of liquid hydrogen, liquefied natural gas, and RP1 using liquid oxygen as my oxidizer. And as expected, liquid hydrogen fuel is probably the least impact among these fuels. Liquefied natural gas impacts human health and climate change more than the other two fuel sources. And then you can finally see that RP1 impacts ecosystem quality and resource areas more than the other two fuel sources. So other fuel sources can be evaluated using this framework to do a quick decision on impact areas and make more informed decisions on which propellant, if you do have a choice for your different rocket boosters for fuel, then this would help you be able to make some of those decisions. So by understanding the environmental or damage assessment areas, it might inform an eco-designed decisions. Next slide. So for electricity or power, I selected two power sources typically found at launch facilities: electricity from the power plant and then diesel generated electricity. The diesel is more impacting across the 4 damage areas. And it's interesting because there was only 224 hours versus 42,000 kilowatt hours from the power plant. So modifying the electricity source can reduce the environmental impacts. I did look at possibly a solar source instead of diesel in my research. Next slide. For the typical chemicals used at the launch complex for the 14 days of operations, it includes chemicals such as isopropanol, helium, liquid nitrogen, and hydrazine. And you can see on this slide, hydrazine is the worst actor across these 4 damage areas. And current research is ongoing now on how to green hydrazine. Next slide. Finally, water for the launch is divided into the deluge water for the rocket engine cooling and personnel water for the 14 days during the launch window. The deluge water affects each of those damage areas more than the personnel water, but this is to be expected because the sheer mass of the deluge water used at the time of launch is at least double that. I also considered and looked at the transportation of the deluge water, and that's what you see here also. Next slide. So finally, from a strategic ELCA perspective, these charts generated through SemiPro, again, version 8.2.3, show the damage areas based on the input for these expendable and reusable rocket. What this view or perspective provides is that it gives a holistic look at impacts of one launch with all of these consumables and how each launch impacts these 4 damage areas. And the scale is relative on the left, the x-axis, because a lot of people ask me, are those real numerical values? They're more in context of the information. But it does give relative values of how each of these consumables compare to each other for that particular launch. For the expendable and reusable rocket example, the propellant is the worst actor in both of the scenarios. And knowing this, then research and efforts can be done to find a more green propellant. And I think NASA and others are working on doing this. And then for the expendable rocket example, the expendable rocket booster is next in the damaging to the 4 areas. So that is probably to be expected as well, because each of those stages, the first stage, the second stage, and the fairing is manufactured and used only one time. So for the reusable rocket example, the chemicals used at the launch complex are second damaging to the 4 areas. So you might take that as an example to start looking at some of the different chemicals used during launch and maybe reduce those, or see if there's another pollution prevention or some other type of opportunity there. This model can be refined if more specific data on launchers and other consumables are available. So after I did all the research and I looked at these results and everything and the impact methodology of Impact 2002 Plus, I wanted to provide an environmental profile for launch. What does it look like when you do this? And I wanted to do something to make it easy, to make decisions easy if people don't have access to SemiPro. And what would it look like if you were to use my framework and my model to be associated with that one launch of the space vehicle. Next slide, please. So I developed the Space Transportation Environmental Profile for Launch. I called it STEP-L. It's an active dashboard It's in an Excel GUI you see here. And I thought this STEP-L dashboard could be used by operators or planners for specifically using these launch examples scenarios I have. It also gives you a system view of the environmental domain at launch. And if possible, there's a way to maybe use it for eco-design for future launchers. Again, it looks similar to the semi-pro output for the 4 damage areas of human health, ecosystem quality, climate change, and resources. And I wanted to show here today for this example for this for our presentation, just to look at a reusable rocket booster with liquid hydrogen, and you can see all of the different aspects here. Now, one thing I didn't mention is when I did the 14-day window, another operational thing are test firings. So test firings is also included as part of my dashboard. Typically that occurs within the 14-day window of launch, and it's mostly referring to the propellant. So you have that added here as well. And there's also some numerical values on the right. Really, that's more of the context of how human health, just the overall quantitative value that you see for human health with all of those together shows. So the base case of one launch using ISO standard 14040 gave insight into damage areas most affected, and it can lead to better eco design decisions. And it also aided in identifying where to focus resources and funding to create a more environmentally and healthy space launch and its total life cycle. So hopefully you can see that this work, this research work I did falls in line with what Andrew's talking about in looking at doing a more comprehensive evaluation of space launches and commercial space, and even looking at all the rocket launches. So I'll now turn it back over to Andrew. Thank you.
Thank you, Sheila. So one question that really has been growing in the space sector is environmental life cycle in itself comprehensive enough or go far enough in our assessment our assessment of sustainability? In this regard, the guidelines for the long-term sustainability of outer space activities actually came out with some very positive statements when it was published in 2017. The first one, paragraph 27.3, actually says that space actors should promote the development of technologies that minimize the environmental impact of manufacturing and launching space assets. That very clearly aligns with LCA and the need to conduct an LCA. But what's very interesting is the paragraph before that, which actually says that space actors should take into account the social, economic, and environmental dimensions of sustainable development on Earth. So does that actually suggest that we should be going towards a more encompassing sustainability assessment, where we're not just looking at the environmental dimension, but also the social and the economic? Now, how would we actually achieve this? So this form of sustainability is what's known as triple bottom line sustainability, where only you can achieve sustainable development through the overarching circles of environment, society, and economy. So on top of environmental life cycle assessment, we would also need to look at social life cycle assessment and life cycle costing. Now, the problem with this approach is that unlike ELCA, which is standardized through the ISO 14040 standards, social life cycle assessment is not standardized, and there is no international consensus on how this should be conducted, particularly in how you can quantify both quantitative and qualitative data in one assessment. Life cycle costing rather, in comparison, is a lot more mature, particularly within the space sector, and there's various parametric, grassroots, or analogous models which can be used for this. But how do we actually combine all of these into one assessment? And the idea with life cycle sustainability assessment is that it's not a model in itself, but a framework of models designed to create more effective decision making in the context of sustainability. So at Strathclyde, we developed a new database called the Strathclyde Space Systems Database, which is world's first life cycle sustainability database of space systems. It contains over 250 datasets that has environmental, costing, and social data attached to it. And the idea is that you can use this database in the design of space missions through concurrent engineering. So as we can see on the right-hand side, this is generally how it works. So in a concurrent engineering environment, you would have many different disciplines which would all feed design data into a central server. In this case, the Open Concurrent Design Tool, which is the European's platform. What would happen is that each of these tools would use the data from other subsystems to come to a design. And through this Stratified Space Systems database, we can extract or export this mission data into our model and use the data sets contained within it to match it up to this design data. In this regard, the database also has a calculation engine. So you can see it's highlighted in blue here because not only has this got an inventory, but it's also a calculation engine. And what we can do is run this to generate life cycle sustainability results. We can then restore this back into the database, and all the other subsystems can then reiterate based on the findings of the SSSD. So what I want to do now is give you an example of 3 studies which we designed at the University of Strathclyde and some life cycle results of these. So these are called MEOS, NEACOR, and StrathCube, which were all designed between 2017 and 2020. So MEOS is a small satellite mission that with a mass less than 300 kilograms, and it aims to collect data on the lunar micrometeorite environment, as well as detect the presence of water content on the lunar south pole in view of a future moon base. Its expected mission duration is about 2 years, and very interestingly, one of the eco-design options they considered as part of this mission was whether we could actually replace hydrazine with a high-performance green propellant, so particularly LNP103S. However, we actually found that despite being marketed as a less toxic alternative, actually when you take a life cycle approach, LNP103S actually performed significantly worse on 13 out of 16 impact categories than hydrazine. So the recommendation, somewhat surprisingly, would be stay with hydrazine. This finding was actually reaffirmed by the European Space Agency through an independent analysis, who ended up finding the same thing. NEACOR, so NEACOR is a low-cost interplanetary mission involving up to 6 12U CubeSats, and the mission aims to estimate the relative position, velocity, and 2D shape of near-Earth objects. The mission duration is expected to be about 4 years and 8 months with a low-thrust propulsion system. And finally, StrathCube is a 3U CubeSat which was developed in support of an internal student-led project. The mission was originally designed with 3 objectives. It has since evolved, but those objectives were space debris detection, re-entry analysis, and to demonstrate wireless power transmission in space. So its lifetime was expected to be about 576 days. These are the example of the absolute life cycle sustainability assessment results at midpoint level. So we can see that we also have whole life cost and social impact as single scores. And overall, these results would suggest that each mission has generally improved as we have gained more knowledge in life cycle assessment. So in that regard, you could actually conclude that since StrathCube is better than both MEOS and NEACOR across all 12 impact categories, it's the most sustainable mission ever built. However, as can be seen, these results look very different when you actually consider the impact per kilogram. So this places an added importance on how life cycle results should be communicated or reported. And this is a topic which we will present with the European Space Agency at this year's IAC. So if you're going to the IAC, look out for that presentation. But looking at these missions, a particular hotspot was found to be the use of germanium as a substrate within the solar arrays. And this was very impactful across the human toxicity and the mineral resource depletion impact categories. So in terms of human toxicity, this was notably due to the release of arsenic, mercury, and dioxins to air from the production and manufacturing process. As for mineral resource depletion, The impact was primarily due to germanium being listed as a critical raw material, since the resource has limited potential of being economically or technologically available in the near-term future. Additionally, also the release of chlorine oxides, nitrogen oxides, hydrogen oxides, and hydrogen chloride during the launch event has a considerable impact on ozone depletion. In fact, near 100% of ozone depletion is driven by this. However, despite these hotspots, it should be noted that the production and manufacturing of the launcher and its propellant would generally dominate the majority of impact categories had a share of emissions approach not been used in the model setup. So in that regard, Neocore impacts were driven mostly by the choice to use a dedicated launcher as part of the mission, whereas MEOS and Strathclyde used a piggyback option. We also used multi-criteria decision analysis to actually group each sustainability dimension into a single score and then into a single sustainability score. And overall, the results would suggest that costs somewhat unsurprisingly produced the highest share of sustainability score across all sustainability dimensions. However, it's very important to note that the weighting of this adds a lot of subjectivity and sensitivity to the results. So before these new normalization factors were added, which are the top bar here, the environment consistently came out as the most impacting sustainability dimension. The old system was what was used in all three concurrent design sessions, so MCDA has to be applied with caution. And additionally, the environmental impact categories do not include several crucial flows due to the high uncertainty attached, such as black carbon and aluminium oxide emissions during launch. However, the aim is to try and update the SSSD in the future so that it becomes even more accurate. So a full list of the assumptions behind this analysis will be released in the extended version of a paper called Life Cycle Engineering in the Context of Aerospace, Preliminary Findings, which should be coming out in Advances in Research, a special issue on space environment management and space sustainability next year. And what I want to do is just sum up here by asking the question, why should you care, or why should the US industry care about ISO 14040 or anything that we have just spoken about? Well, simply, there is an obvious risk to US manufacturing here. The United States is currently the leading net exporter of aerospace products globally, with the European countries providing the largest single destination market amongst US manufacturers. Actually, in 2019, the US's largest export to the EU was aerospace products and parts, valued at about 35.7 billion US dollars. However, within the European space sector, as I've gone over previously, the application and perceived importance of this is exponentially growing, and it's now become a common part of many procurement processes. In fact, the European Space Agency have this as a mandatory element within several of its space missions already. And as such, it's a distinct possibility that the technique could become a mandatory part of the procurement and space mission design process within Europe before the end of the decade. In comparison, very little work on LCA space assets has actually been conducted in the US, and that means that the US has started to fall behind others on this front. This could become quite a serious problem for manufacturers in the near-term future due to misalignment or non-compliance with European procurement policies. And this has the potential to cause widespread supply chain disruption across the US. Therefore, a properly managed supply chain with the ISO 14044 standard at its core immediately helps to mitigate these potential impacts and risks, whilst allowing the United States space sector to become fully accountable within their operations and begin to champion LCA. In that regard, we have created a list of recommendations to try and advance this a little further within the United States. So firstly, we would like to see the creation of a set of guiding principles for the application of environmental life cycle assessment of space technologies in the United States, and also a tailored database and eco-design tool which is suited for the United States manufacturing, production and materials and processes. Really, to achieve this kind of framework, which is kind of similar to what ESA have already done, a consortium should be developed which is composed of US space companies, national agencies and support companies to help establish space LCA within the country. and also provide relevant information or data sets on the manufacturing and production processes. And ultimately, this should then be fed to NASA or Department of Defense contracts, including those issued externally to US space manufacturers, launch providers, and their major suppliers. So before we close for some discussion, just to summarize, over the last decade, we've seen environmental life cycle assessment starting to grow in importance amongst European industrial stakeholders and national agencies. However, due to the specificities of the space sector, the methodological rules within the ISO 14044 standard required some adaptation to make it more suitable to our space and for it to actually be widely used in the space sector. But we have found that with the appropriate adaptation, environmental life cycle assessment has already been successfully demonstrated, including within the studies we've already seen today. And that reaffirms not only its importance, but its appropriateness as a tool to scientifically quantify and then reduce adverse life cycle environmental impacts. It's also important to say that this is applicable not just from a European level, but also in the United States itself. But it would require the implementation of a framework similar to what has already been done in Europe. However, the US is starting to fall behind others, and they must catch up if they don't want to lose the space race on ELCA. So I firmly believe that the US can start championing this, and this is a call for them to start at now. That is it for our presentation, so I'd be happy to open the floor up for discussion. If anybody is interested in contacting us further, our email addresses are on screen right now. Thank you.
Thank you.
Thank you, Andrew. Thank you, Sheila. We do have a few questions. We have a question from Daniel Smith. I wonder if the ELCA specifically applied to space is uniformly adopted across governments and also across private and public spheres. How uniform then is the ELCA application for space, do you think?
Okay, so really, environmental life cycle assessment is quite new and is still developing in Europe. Okay, it was only adopted in 2009, which is quite late for life cycle assessment, considering it's been around since the early 90s. It's really been driven by the European space sector, but at the moment, and I don't see it changing, life cycle assessment itself is a voluntary tool. Okay, so there's nothing that actually enforces its development, apart from if there's environmental reporting requirements, which is what the European Space Agency has conducted. Now, most of the work in Europe has been done by kind of larger companies, but because the European Space Agency, which is kind of the largest in Europe, or kind of the go-to for space there, it's really kind of dictating how ELCA will develop, basically. There's going to be a paper at the IAC which actually looks to advance this into formal environmental declarations. So basically avoiding greenwash, avoiding false environmental or unjustified environmental claims. But in terms of national government, it's not quite at national government level yet. It's not quite got out of Europe too much yet. I'm aware of some studies in Australia and New Zealand, but really it's mostly just European at this point in time. I think from an EU level, there is definite interest. So I've heard of interest in developing what's called product environmental footprint category rules for space LCA from the European Union or the European Commission. So there is the interest there, but it's still very early days.
And so I'd just like to add from the US standpoint, I know when I was doing my research, I reached out to NASA and some of the other rocket launch companies and things like that. And most of them either didn't know what an ELCA was, or they weren't really looking at it as part of their business practices. So that was one of the things that I noticed, and that's why I really wanted to do the research and reached out to the ESA Clean Energy as well, because they had been doing a lot of work. But from a US standpoint, I don't think we're even doing anything from that perspective, from a US standpoint.
Thank you. That's really interesting to compare. But I guess generally speaking, one could say that the European Union is always a step ahead when it comes to environmental regulation, right? We have another question, or a couple of questions from Mike Ray. Mike, let me know if I'm not posing your question correctly. He says, I understand environmental assessments do not provide cradle to grave understanding. Are there any efforts to consider the problem of space debris problem from the perspective of ELCA?
Yes, simply put, yes. One of our, so when Sheila and I were doing our PhD, we were actually part of a small student consortium where there was actually somebody else who now works at the European Commission called Dr. Thibault Moury. He worked with Airbus and at the University of Bordeaux. And his entire PhD was dedicated to integrating the issue of space debris as an impact category indicator within life cycle assessment. So he looked at it in terms of orbital space, looking at space as a resource and orbital resource depletion, basically. I'm not going to speak too much on his work because at the minute, the European Space Agency's position is to keep space debris as a separate issue for now. But that work has already got underway, and personally, yes, I do see space debris being a completely separate impact category as part of life cycle assessment. So yes, that has started.
If I may follow up on that question, why does the European agency keep it a separate issue?
So, firstly, it's because life cycle assessment generally characterizes impacts within different impact categories, right? So Sheila presented endpoints, I presented midpoints. So these would go towards climate change, acidification, ozone depletion, etc., etc., etc. So it needs to be its own impact because it won't fit into any of these impact categories, right? So it's its own impact category. Now, the reason it's not currently being included within the LCA framework is because at the moment, well, for two reasons. One is because the work that has gone into this is not yet fully completed. It's taken Thibault about 3 or 4 years to actually get to anything that's usable, and it's not yet complete. And secondly, is because the European Space Agency actually consider space debris to be covered by their space debris verification guidelines. I can't remember the number of these the guidelines. So under the Clean Space Initiative umbrella, they look at active debris removal, they look at design for demise and various other issues. So it is captured within the work they do, but at the minute LCA it's still kind of developing, and I would say it will probably not likely to see the indicator being widely used for at least another handful of years until it matures a bit more.
Okay, we have one last question from Nicholas Pender. With the coming rapid reusability of Starship and its super heavy booster, will it be worth comparing the life cycle of fully reusable rockets with airlines?
So I'll just field this question first, I guess. But when you ask the question, fully reusable rockets with airlines, are you talking about doing a life cycle comparison with commercial airlines versus these these super heavy boosters, Starship? Is that what you're saying? You are? Okay. Yeah, it would be interesting to see that. It'd be interesting to see how the manufacturing and all the other the raw materials and even going into the disposal aspect of it, just the full total life cycle. So it would be worth comparing that. Andrew, do you have anything on it?
Yeah, from my perspective, it depends if you're talking about Starship and you're talking about intercontinental point-to-point travel, right? The space industry is going by current trends, is going to scale up, right? So we conducted an analysis at Strathclyde, and it actually kind of shows that at present the space sector's impact in terms of annual global emissions and also in terms of planetary boundaries, so the ecological threshold which the planet can sustain, is actually pretty low at the moment. But we also looked at a future scenario where we scaled up industry operations. We looked at space tourism. We looked at Moon Mars colonization. We looked at the introduction of mega constellations where launches increased about 7 or 8 times than what they are today. And the impacts become a lot more meaningful and a lot more significant. So yes, I do think that if we're going to be talking about scaling up the number of launches in the future, then yes, a conversation we absolutely have to have. On top of that, according to the Greenhouse Gas Protocol, black carbon is not considered general within greenhouse gas accounting tools because of the high uncertainty attached, and because generally, if it's released from ground, it would kind of phase out of the atmosphere very quickly. But there's research to suggest that actually black carbon emitted directly into the atmosphere by rockets could have a very damaging impact. In fact, one paper I read very recently actually suggested that currently it could actually create CO2 levels that are about a quarter of current aviation. Now, I'm not exactly sure it's going to be that high, and that result had a lot of uncertainty, so research will need to go into this. But yeah, I think absolutely this is a conversation we need to be having, and it's something that does need to be addressed, particularly if we're going to be looking at intercontinental point-to-point travel, mega constellations, space tourism, Moon or Mars colonization, etc., etc.
Okay, well, I don't see any more questions, so I believe we can wrap up. Thank you very much, Andrew, and thank you very much, Sheila. This was a very interesting presentation. I learned a lot, and I think the audience enjoyed it. So we hope you will all join us for our next panels, and thank you again.
Thank you.
Bye-bye.
Bye.
Right, thank you.
Thank you, Andrew. You did a great job.
Thank you. It was, yeah, it was.
You did.